Okay, good afternoon, everyone. We'll continue today with Coulomb's law. Here we'll be looking at more examples for Coulomb's law. Here we have two protons inside a helium nucleus that have a typical separation of 3 × 10⁻⁻15 meter. What is the electric force between these two particles? So, if we are to solve for this problem, then we have here two protons. Every one of them has a positive charge, E. They have a distance of 3⁻⁻15 meter. So this is the distance R. We need to calculate the force. So if I am to call this one Q1 and this one Q2, in this case, those two protons, they have the same charge, positive charge. This means this one will be F due to 1 on 2. And if this one is green, then this one will be F21. And as you know, F21 vector-wise equals to minus F12. Magnitude-wise, they are the same, and they equal KQ1 Q2 divided by R squared F21 as this is 8.99 10⁻⁹ times 1.602 ⁻⁻19 squared, because the charge Q1 and Q2 are the same, divided by 3⁻⁻15 also squared, and in this case F21 equals to F12 equals to if no other forces are acting, what is the acceleration experienced by one of these protons? Mass of the proton is 1.67 10⁻⁻27. So we know mass is 1.67 10⁻⁻27 kilograms. We need to calculate the acceleration. We know that F equals to ma. So if I take Q1, then I will be looking at F21. Let me take my coordinates to be X and Y this way. This means F21 equals to M, which is 1.67 10⁻⁻27 times A, and A will be pointing toward the west because F21 is pointing toward the west. So I have A equals to F21 divided by 1.67 10⁻⁻27, or A, as 25.6 divided by 1.6710 to the power minus 27 meter per second squared. Vector wise, as I said, 1.54, 28, and this is going to be west. So in this question, we have the following picture, as you can see, and this is very common when we have an electrostatic being transferred due to the rubbing between two materials. Here, for example, this child is riding on the slide. The slide is made of plastic, and as you can see, while he was sliding down, his hair became, as you can see, pointy. Why is this happening? We have here three options. Either the charge builds up on the child through transfer of electrons during the slide, or a charge builds up on the child through transfer of protons during the slide, or his mother did not brush his hair. So we have two answers that we need to eliminate one of them. We know that the only particles that can transfer is the electron. So electrons in this case will be transferred from one to another. Protons do not transfer. Protons are locked up inside the nucleus. That's why the electrons are the one that transfer. When they transfer from one object to another, they make one of them more positive while they make the other one more negative. So the answer for this phenomenon is A. A charge builds up on the child through a transfer of electrons during the slide. Now let's solve this example. In this example, we have three charged particles: an electron, proton, and an alpha particle, which is a helium with two protons, are arranged as shown. What is the resultant force on the proton P due to the electron and the alpha particle? Okay. So let's draw first the free body diagram. We have here, we have the alpha that I'm calling Q1. We have the proton that I'm calling Q2. And then we have the electron that I'm calling Q3. Now, the alpha here is equivalent to two positive charges. Proton is one positive charge, and here the electron is a negative E. So if I am now to draw this is the lines between them, extending this one, I have the angle here as as 55 degrees. So in this case, if I am to draw the force due to Q1 on the Q2, then I will paint this one with blue. And this now the force, because both are positive, the force is going to be pointing in this direction. This is F1, 2. And now if I am to paint this one with the green, then because now those charges are opposite, then the induced force will be attractive. Then F due to 3 on 2 would be this. Now my coordinates are given to me as X and Y. So if I want to calculate uh, those forces, I'll start first with the F12. So I have F12, that's equals to K Q1 Q2 divided by R squared. So I have F12 equals to 8.99 10 to the power 9 times the charge of the alpha is 2e, which is 2 times 1.602 10 to the power minus 19, and the other one is also 1.602 10 to the power minus 19 divided by r squared. The distance here is 1.4 10 to the power minus 10, and the distance here is 1.2 10 to the power minus 10 meter. So divided by 1.4 10 to the power minus 10 squared, and in this case F12 becomes 2.35 10 to the power minus 8 Newton. What about F32? F32 equals to, again, Q1 is a proton, so I have 8.99 10 to the power 9 times 1.602 10 to the power minus 19 times, this is electron, however, I'm taking a magnitude, so it's 1.602 10 to the power minus 19, and all are divided by 1.2 10 to the power minus 10 squared. And in this case, I have F32 equals to 1.6 10 to the power minus 8 Newton. So this is the second force. Now, if I want to calculate, I need the total force. In this case, I have to project the F32 on the X and on the Y. I cannot add them mathematically this way. I have to find the X component and the Y component. So this is the X, this is the Y axis here. Then I have this F32 is projected. This force is F32X, and this one is F32Y. Then F32X as 1.6 10 to the power minus 8 times cosine 55 degrees, which means F32X equals to 9 to 10 to the power minus 8 Newton. And then F32Y is 1.6 minus 8 times sine 55 f32 y equals to 1.31 10 to the power minus 8 Newton. Now, my F total x is F12 plus F32x. F dot x equals to F12 2.35 10 to the power minus 8 plus 0.92 10 to the power minus 8, and F dot x becomes F total x as 3.27 10 to the power minus 8 Newton. F dot y as equals to F32y, F dot y as 1.31 10 to the power minus 8 Newton. So F dot as 3.27 minus 8 squared plus 1.31 minus 8 squared, and F dot equals to 3.5 10 to the power minus 8 Newton, and theta is tan inverse of 1.3 to the power minus 8 divided by 3.27 to the power minus 8, and theta is 21.8 degrees. Now let's look at this example. In this example, we have three charges as well. We have one of them positive 1 microcoulomb. The second one is 1 microcoulomb, however, negative, and those are applying force, or we want to calculate the overall electric force acting on the negative charge Q1 due to the positive 1 microcoulomb and the negative 1 microcoulomb. We need to find the direction. So this we should be able to do it by inspection, because as you see, the magnitude for the force exerted by the positive 1 microcoulomb should equal the magnitude of the force exerted by the minus 1 microcoulomb, because at the end I'm taking the magnitude. When I can do the calculation, the Q will be the magnitude. So in this case, we'll start with the positive 1 microcoulomb. Then the force here will be attractive, because this is positive and this is negative. So the force will be attractive, and let me draw the force to be this way. However, because both of those two charges are negative, then the force will be repulsive. Will have the same magnitude as this force, however, will be in this direction. Then if I am to calculate the total force due to those two forces, remember this is 90 degrees, which means that this is also 90 degrees. In this case, the summation of those two forces will have a zero y component. However, all of them will be on the x component pointing in this direction, as you can see. And now the answer to this one would be D.